We have developed a handheld haptic device capable of displaying force and giving stretch feedback to a user in virtual environments. It is made of 3D printed parts and off-the-shelf components. The user holds the device from its handle and inserts their thumb and index fingers in the thimbles, as shown in the video. On the handle, which is held in user's palm, a rubber tactor moves in radial, ulnar direction to stretch the palm skin to display stretch feedback. One of two DC motors inside the handle actuates the cable-driven mechanism of the rubber tactor. The other motor provides force feedback via a separate cable-driven mechanism to render rigid or soft virtual objects. In this mechanism, two sliders move in the opposite direction, simulating the grasping of a virtual object with index and thumb fingers. Thimbles are attached to sliders with bearings, providing the user with a passive degree of freedom for more comfortable use. Force-sensitive resistors placed inside the side walls of each thimble measure the forces applied by the user's finger. A PID controller is utilized to minimize the error between the measured and desired forces by adjusting the motor's rotational speed. Closed-loop force control enables the rendering of virtual objects with different stiffness values. The controller board of the device connects to the computer via serial port. We have conducted two sets of two alternative force choice experiments to evaluate the stiffness rendering performance of the proposed device and to show that the range of object stiffness perceived by the user in virtual environments can be significantly expanded by controlling the relationship between the visual and haptic cues. In the first set of experiments, the participants were asked to discriminate the stiffness of two virtual objects using haptic cues with or without a visual display of the haptic displacements. There were, in total, 7 stiffness pairs. Participants were asked to discriminate the object stiffness by squeezing them with their index and thumb fingers and judging which one was stiffer. From the resulting psychometric curve, just noticeable difference values were calculated as 7.24% and 10.41% for with and without visual feedback, respectively. In the second set of experiments, the visual feedback displayed to the user was manipulated to create a conflict between vision and haptics. The degree of manipulation is defined by a parameter lambda, where a value of 0 means no conflict, while a value of 1 means a complete mismatch between visual and haptic feedback. The results show that the participants essentially paid less attention to kinesthetic hand position information regarding object deformation and based their judgment on the relationship between the visual position information and the squeezing force sensed haptically. These results imply that despite the physical limits of a force feedback device, rendering virtual objects with a larger range of stiffness is possible by altering the visual cues, and a single variable, named Apparent Stiffness Difference, can predict the pattern of human stiffness perception under manipulated conflict.